This is the example on slide 6 of our chapter 20 part 2 PowerPoint. And here we are asked to find or to calculate the K, or equilibrium constant, for the oxidation of copper by hydrogen ions. So they have the equation written for us, and we're going to be using the equation relating our standard cell potential to our equilibrium constant written on the slide here, as well as the standard cell potential calculation from each half reaction. So kind of similar setup to the problem that we just worked together, the previous problem on slide 4, at least in the first part, but now we're using a slightly different equation to ultimately calculate our equilibrium constant K. So first things first, we need to figure out what's oxidized and what's reduced in our reaction so that we can correctly split it up into its half reactions. So copper solid by itself has an oxidation state of 0, hydrogen plus 1, copper 2 plus is plus 2, and then hydrogen gas by itself is 0. So copper is being oxidized from 0 to plus 2, and hydrogen is being reduced from plus 1 to 0. So first things first, I'm going to write my oxidation half reaction. So remember, oxidation occurs at the anode, and it's going to be copper solid reacts to form copper 2 plus ions plus 2 electrons, and the standard electrode potential for that, for our anode, if you consult your standard electrode potential table, is 0.34 volts. And then for our reduction that occurs at the cathode, it's going to be 2H plus forms plus 2 electrons forms H2 gas. Because remember, that's a reduction. In reductions, electrons are written as a reactant, and in oxidations, electrons are written as a product. So the standard electrode potential for our reduction, if you consult your table, this is actually the standard hydrogen electrode, SHE, and it corresponds to a value of 0. So then we can add these two reactions together and perform our E-cell calculation. So when we add them together, our 2 electrons on each side cancel, and we are left with hopefully the same reaction that we have written up top. This is just a way to check ourselves, to make sure that stoichiometrically we're transferring the same number of electrons between reactants and products. This will become important in the next couple problems when we start using the Nernst equation. So our standard cell potential, it's going to be our cathode electrode potential minus our anode. So it's going to be 0.00 volts minus 0.34 volts for a standard cell potential of negative 0.34 volts. So we have that value. Now we also need to figure out what N is. Since we transferred 2 electrons, our N, number of moles of electrons transferred, is also 2. now we have all the values we're going to need to plug into our equation. I'm going to transfer to the next slide. I have everything written, ready to work. So before we start plugging stuff into this equation, I'm going to rearrange it so that K is by itself. So that means multiplying by N and dividing by 0.0592 volts on each side times N divided by 0.0592 volts. So that our new equation is E, I'll write K on the other side, is log of K is equal to our standard cell potential times N over 0.0592 volts. So now we have everything ready to plug in. So that's going to be equal to, let's see, log K is equal to negative 0.34 volts times 2 over 0.0592 volts. Our volts are going to cancel, which is good because we want our K to be unitless. And if we multiply all that together, we get that log K is equal to negative 11.486. So we're not quite done with this problem yet. We still got to get rid of the log in front of the K, so we just have K by itself. And if you remember from pH, the way to get rid of a log is to take it 10 to the whatever power. So 10 to the whatever gets rid of the log K, and K therefore is going to be equal to 10 to the power of negative, here I won't write the little caret top, negative 11.486. And if I plug that in, it should give me 3.3 times 10 to the negative 12. That is our K, and that is coincidentally our final answer.